Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Hydrolysis and decarboxylation of beta-keto esters. Moving on to the next step. The starting material is ethyl 2-oxocyclohexane 1-carboxylate, which is a beta-keto ester. The ester group, CO2-ate, is at C1 and the ketone carbonyl is at C2, the beta position relative to the ester. Moving on to the next step. Treatment with aqueous acid hydrolyzes the ethyl ester to give the corresponding carboxylic acid, 2-oxocyclohexane 1-carboxylic acid. This is a beta-keto acid, where the carboxylic acid is beta to the ketone carbonyl. And for the final step, beta-keto acids readily undergo decarboxylation upon heating via a 6-membered cyclic transition state, enol intermediate, losing CO2. The carboxylic acid group at C1 is lost as CO2, leaving a carbanion enol at C1 that tautomerizes to give cyclohexanone. The product is simply cyclohexanone, an unsubstituted cyclohexanone ring. This corresponds to option B. Why other options fail? A. To form cyclohexanone would require reduction of the ester to an aldehyde, not what H3O plus delta does. C. To methylcyclohexanone would require the ester to become a methyl group, which does not occur under these conditions. D. Cyclohexane 1,2 dione would require oxidation or a different reaction pathway. Decarboxylation removes the C1 carbon as CO2, not retains it as a ketone. Therefore, the correct answer is B. Therefore, the correct answer is option B.